sense? You're not getting confused with the dizzying array of clustering methods that I've been throwing out there? That's good. I'm going to give you one more today. All right. So let's talk. Let's go back to what is, in my view, another interesting way of thinking about clusterings that is not as common as some of the others, but is very much. I see it appear often when people think about how they do clustering, but I don't see it explicitly spoken out as much. So what I want to do is tell you what to say. And this is, in some sense, the information theoretic perspective on clustering, or rather, to put it more casually. So we've seen, clustering as grouping, which is the most common way of thinking about it. Clustering as separation. We've seen clustering as, likelihood estimation, density estimation. But we haven't, at least in my mind, we haven't really seen the notion of clustering as compression. And what I mean by that is let's go back to the whole idea of Occam's razor. The whole principle of Occam's razor was that you wanted a succinct description of your signal, of your data. Right? And we've seen that when we talked about how to choose k, we use this intuition as a way to think about the right k to choose by saying, okay, we want to somehow not choose a very large k because that somehow means that you're using too superfluous a description that could overfit your data. And obviously you don't want it to be too small because that would be noisy. So you have to trade off between these things. Right? And so k was the measure of complexity we want to optimize, and we did all this AIC, BIC stuff and said, okay, there's some kind of scale factor. There were two terms. We said, okay, you want to minimize some error term plus some constant times k. And if you remember when you looked at the Akai K information criterion, the Bayesian information criterion, this constant changed, but the form of this expression was the same. It is some kind of combination of these two things. Right? And that assumed that this was the right way to think about the compactness or the way to describe the clusters. And it turns out that maybe this is not necessarily the best way to do this, because first of all, as I pointed out, these are the wrong units in some sense. They don't really match up. So how you scale them together, it's not really clear. And maybe there's a way to kind of harmoniously balance these two terms, so they both can be expressed in the same units. And it turns out there is a way to do that. And that gets you into a very information theoretic view of clustering, which is very elegant in its own way. And in some sense, requires less information about your data than you think you need. And it's kind of cool. So let's talk about that. And what you end up with this idea is the idea that when you're clustering data, you're not talking about, grouping or significance or latent variables or likelihoods. You're talking about compressibility. And in some sense, if a cluster looks like this, let's say a cluster looks like this, right? It's somehow compressible. I can isolate small clusters here, and that's going to be okay. But if a cluster looks like this, it's kind of incompressible, that any description of this, you might as well just write down every element in it. You're not going to get any benefit from there's no succinct way to describe what's going on. It just is what it is. Or this is not maybe the best way, this is full. Like, if it's only random in this case, right? And in some sense, something that's purely random, there's no easier way to describe it than just by itself. And those things are incompressible. And so the information theoretic view is trying to find some of these incompressible cores of the data. And this is not just an information theoretic perspective. There's also what is called a Kolmogorov complexity perspective, which people have used to try and do clustering. And this is a little bit more intricate. One way to think about the difference in these two things is that the information theoretic viewpoint talks about entropy and mutual information and things like that we'll talk about. The Kolmogorov complexity viewpoint talks about the length of the shortest program required to describe the set. And this is a little nastier deal. Most of the problems here are undecidable. You can't really do anything with them. But there are ways to get around this, and these two are very similar. So I won't yet talk about this. There's not really much I can say except for the basic intuition. But I will want to talk about this today. The information theoretic view on clustering. And because it's information theoretic in some sense, it allows you to remove information from the data. You actually, surprisingly enough, you don't need things like distances. You don't need a metric space. You don't need any kind of information about the data. That's kind of weird, but it still works surprisingly well. We'll see how it goes. Okay. But before that, I feel it might be useful to do some background on information theory itself, because probably not everyone in the room is familiar. So how many of you are very comfortable with things like entropy, mutual information, Kullback-Leibler divergence, and stuff like that? How many of you are reasonably comfortable with that? How many of you define mutual information right now if I asked you to do it? Okay, good. So then this will not be wasted. So in all of what we're talking about, we're going to start off with a distribution over some finite ground set. So there'll be some finite ground set, and just for a lack of a better term, this finite ground set will be the set of all objects 1 through n. Okay? So if you think of a distribution over this finite ground set, you can describe it by a set of probabilities. Right? So there's probability P1, so there's probability P1 up to Pn. Right? So this will be the base object we always deal with, some kind of distribution over a finite set. It doesn't have to be finite, just makes things easier. I don't use integrals and stuff everywhere and things that you're bounded. So, and then, so you have this thing. And the first thing, of course, you want to know information theoretically, the first thing you learn about a distribution is its entropy. Right? And so if we call this distribution P, right, described by these probabilities, then an H of P is defined as this quantity. Okay. There are many good and deep reasons why the entropy should be defined in this particular form. I won't get into any of them. It's a very nice sort of way to think about a discussion to have. When Shannon first came up with this notion of entropy, there are good reasons why this is the right form of that expression. Nevertheless, this is an expression that in some sense captures something about the amount of information in that distribution. And in one way to think about this is that it's equal to the expected number of bits to describe an element or a sample from the distribution. Right. And you may be thinking, what on earth does that mean? I have n elements. So I need log n bits to describe them. The entropy should always be log n. And you would be correct in one sense, that yes, with log n bits it suffices to describe every element of the space. But we're trying to capitalize on the fact that some elements are more frequent than others, or some elements are rarer than others. And so if you think of this, right, what you're saying is that this is the expected value of this weird quantity, log 1 over pi. That's another way of saying this with respect to distribution. So if you take an element at random, the probability you see it is pi by definition. And then you need, what it's saying is you need these many bits to describe it. Right? And that could be much less than, the overall number of bits you need could be much less than log n. For example, if all your distribution was concentrated at one point, right, your distribution consisted of, suppose P was P1 equal to 1 and everything else is equal to 0 because they have to sum to 1, then the entropy of this distribution is 0. What's saying is that there is very little information required to describe. You just know what it is. It's always the first element. There's nothing you need to know to describe what the element is. So the entropy can be much less than log n. It could be very different. And so this is the intuition that it should capture this thing. Of course, we know that it's more than intuition. There's actually an algorithm that gives you exactly this encoding of your data. It's called Huffman coding. And I just want to go through it because it's useful to sort of think about what's going on. And we've seen this I think at least in some variants of the algorithms class that I teach, we cover Huffman coding. Because it's a very simple algorithm to do this. If you have a distribution and you have these PIs, and you say, I want to build the right encoding scheme to get me, in fact, exactly this property. Does anyone know what we do? What do we do? Yes?
So it's very simple. You compute the probabilities, the relative frequency.
Well, I have all that. Yeah, I have them here.
And so then you start at the bottom.
Yeah.
Start with the least frequent.
Yeah.
And you put it together.
Yeah.
And put it together. And so on.
So it's like a hierarchical clustering, right? So you take all the properties at the bottom, P1 through Pn. You take the pair that's the smallest. Okay. So maybe just for convenience, this is first two. So you connect them up. Right? So now you get a new object here, whose value is now P1 plus P2, and you have the rest. Now again, you take the two least frequent items, whose sum is the least, put them together. It might be this, it might be something else. So maybe it comes something like this here. maybe comes like this, and then maybe this comes like this, and maybe this comes like this, and then you're done. Okay? And at the end, what you say is that I'm just going to label, this is a binary tree, so I'm going to label the edges of the binary tree with zeros and ones. So the left side is always 0, the right side is always 1. Okay? And now the encoding for any object is you go down the tree to the where it is. So let's say you're looking at this element, 0, 1, 0. So the encoding of this element is 0, 1, 0. Now what's going to happen? Which elements are going to be further down in this tree? The elements that got merged first. But the elements that got merged first are the least frequency, which is good because the things that have the smallest frequency, you can afford to spend more time, more space encoding because you're not going to see them very often. The things that occur very frequently are going to show up right at the end, so their encoding is going to be very short. And that's what you do want because they're showing up very often. You don't want to waste time. So you adaptively change the encoding length based on the frequency of the elements. And this is what is called a prefix-free code, which means that no code is a prefix of any other code. Yeah, and it's because they're all leaves at the bottom. And so you can always decode this associative string. And you have to, it takes a bit of work to prove that this bound, the expected size of what you get. So the expected size of a code word, so if you take a thing at random according to this distribution and look at its code size, so the expected code word length is basically, and you subtract it from HP, it's off by 1. So it's not exactly right, but it's off by 1. And there's a more sophisticated version of this called arithmetic coding, which can do slightly better. There's another version of this called arithmetic coding.
Completely impossible to do it in practice.
That may be. But it's not so bad actually.
When I study the things, that's such a mess.
So why am I saying this? I'm not, you'll see in a second why I want to explain Huffman coding to you. The important point is that the entropy of a distribution gives you a way to express, in some sense, the information content of the distribution in this form. And there's an explicit way to construct such a coding. Okay? Yeah.
So this Huffman coding is for when we have the whole data set?
Yeah, when you have all the
set of
frequencies.
items,
When you have all the frequencies.
And you have all the frequencies.
Yeah.
Is there any version of it for
In the stream? I was thinking the exact same thing as you asked that. I suspect there is. I don't. So the problem, of course, is that your output size is going to be very large. Right? For every item, you need to output a code word. So in the stream setting, what does that even mean? I'm not allowed
No,
to.
let's say that the domain of the items that we have is fixed, but
If it's fixed, I can just count all the frequencies out.
So,
No. The domain of the items that is going to appear in the string is fixed.
Ah.
But as we go in the string, the frequency of the items is going to change. Is there any dynamic version of constructing this string?
Yeah.
My feeling is that in the domain of the, if you're told that only k items will show up from universe of size u, where u is very large, and you want to compute a code word for them, then you need some appropriate hash function. Then just run everything through a hash function first and then run it. So the hash function will make sure that your items sort of go to the bottom k bins, keep k bins around. So you need something like, I don't know, maybe you keep k squared bins around, take your items and hash them in, so you'll get a collision-free hashing, and then build your Huffman coding thing on that thing. So that's my first approximation for an algorithm to use in a string. Because the hashes are linear, you can do this as with updates. That's what I would, whether you can do anything better, probably, but this will be the first thing I would try.
So what the algorithms for zipping and compression do, like deflate and this, they use exactly this thing. So they look at a certain window, and they do the constructed Huffman coding, and then when those probabilities change a lot, they just update the Huffman coding and go from there on.
So it
So it's
falls
like-
in the category of window-based kind of.
Yes.
We know what?
Window-based. kind of.
Window-based, yeah. Well, yeah, but you don't. I mean, you don't want a window-based method, though. You want to get the whole aggregate set, right? You don't want to delete things. Window-based should be deleting frequencies.
No, it's not deleting, it's just updating them.
So updating.
Every so often you have the updates of it, if it has changed.
Yeah, so as long as you have some kind of, I mean, if you use a hash function, it's linear, so I think you should be able to do this update very easily. So, but it's a good question. I have to look it up and see. If you Google streaming Huffman, you might find something. So, yeah. Okay, so, right, so and this is a good point also because it assumes that you know the frequencies ahead of time. And it also assumes that they're correct. That you actually, you have the when you build this thing, that these are in fact the correct frequencies that you have. But suppose they aren't. In other words, suppose that you have a distribution coming at you. Okay, so let's take the new setting here. So now again I have a distribution coming at you. I have things coming in. And this distribution is P. Okay? But I didn't know that. I made a mistake. I thought it was Q. And I have Q. Yes?
It's called adaptive Huffman coding.
So what is the method?
I don't know, but there's a whole Wikipedia article on it.
There you go. Once again, Google saves the day. Or Wikipedia saves the day.
Well, Google got me the Wikipedia article.
Okay. A joint project in Google and Wikipedia saved the day. But yeah, so I imagine something like it had to have been done. So.
Do you have also some paper in accurate coding the same information?
Sorry?
Right?
What?
You have also some.
I do, but that's not for Huffman coding. That's to compute the entropy. So the problem we were looking at is if you have a stream of items and you want to compute the entropy of the stream, how do you do it? Because you don't have, because the frequencies, you have to you can't maintain all the frequencies. And so then, we had this one paper, then there was a series of work, and then this problem has finally been killed. It's like, we know exactly how to do this and all update models and everything. So there's this nice paper by Kane, Nelson, and Onak that solves this problem basically to death. So that's a nice question. Yeah, but it's not this problem. It's not actually. Okay. So suppose you don't know P, you actually thought it was Q. So when you built your Huffman code, you built it based on Q. So an item I came in from the domain 1 through n, you said, okay, its frequency must be Qi, so I'll build the tree accordingly. But actually it was P. So obviously you're going to make some mistakes. Right? And you can work out exactly how much the mistakes are going to be, because what you're going to see is that you're going to use, for item I, you're going to use log 1 over Qi bits for it. Right? Because that's what you think that you're supposed to be using. But the item occurs with probability Pi. So the expected, the amount of space you expect to spend on an item is going to be written as, so the algorithm will spend something like sigma Pi log 1 over Qi bits on average for an item. Because it will use log 1 over Qi based on the Huffman coding or whatever. But the element only occurs Pi times, or a fraction of times frequency of Pi, right? What it should have been spending was this. Right? So this is the excess, the amount of extra that you're spending because you made a mistake. So if you calculate this expression, this could be written as some of you may find this expression familiar. This is called the Kullback-Leibler divergence, KL divergence, relative entropy. This is probably the most fundamental distance notion in information theory as a way to compare two distributions. It has many ways you can think about it. One way to think about it is the error in your Huffman code when you try to encode using Q with the distribution actually was P. It's not obvious this number should even be positive, but you can show it. This is a very fundamental lemma, and it's called the data processing inequality. And you can show this thing is positive. There are many ways to prove this. The way I like to think about it is that this is an example of Bregman divergence, and therefore it's positive. That may be too much of a heavy hammer. There are other ways to show it. But the point is that this thing is not even symmetric. Notice that, right? It's asymmetric in P and Q. Because saying, what is the error involved in thinking it was Q and it was actually P? It's not the same thing as the error involved in thinking it was P and it's actually Q. For example, if you thought the distribution had no probability for, say, item 1, so you thought it was Q and you were not going to see item 1, and item 1 showed up, you would have no way to encode it. Your tree could do nothing with it. And if in fact you put this number in here, Q would be 0, this number would be infinite, be undefined. Whereas the reverse is not true, right? If you didn't see a Q and you're encoding, I never saw a Q, it's fine. Don't care. So there's a natural asymmetry that needs to be there in this definition. But this notion is important because this is a way of capturing the distance to another distribution. The distance from P to Q. So we'll often write this as D of P Q to signify it's an asymmetry. Okay. All right. So two important notions. First of all, secondly, the notion of distance in distributions, and of course, firstly, the notion of entropy of a distribution. Again, what we're doing right now is building up a toolkit of concepts in information theory that will be useful in interval clustering. And we have to do this because we want to get comfortable with these intuitions. Otherwise, the way we use them to do clustering, I could give you the formulation of the clustering problem, would make no sense whatsoever. It would just be completely random. So now we understand what these two things are. Any questions so far? Okay. So the next thing, the last thing we need to understand is mutual information. Okay. There are many ways to define the mutual information, and it's defined in terms of a random variable. So you can think of P as a distribution, or you can think of P as a random variable. So a random variable defined over 1 through n has probability P1 of being 1, probability P2 of being 2, and so forth, and so on and so forth. And so technically, I should be defining the entropy of a random variable, not of a distribution, but these are minor things. But when we get here, it's a bit better to keep track of these things. So suppose I have two random variables, x and y. Okay, let's say they're somehow related in some way. I don't yet know how, but they're somehow related. There's some amount of information leakage between the two. So I can try to quantify this notion via mutual information, which I will define in the following way. The mutual information between x and y. And I'm going to put a semicolon here. It's just a convention. It's a symmetric notion. It's not asymmetric like this is. I'm going to define it this way. So I realize I should have defined conditional entropy first. So maybe I should do that first. Let me first define conditional entropy. So what is conditional entropy? So I know what entropy is. So what is the conditional entropy? Intuitively, the conditional entropy. So we know that entropy of a variable you can think of alternately as the information content of a random variable or the uncertainty in a random variable. Either way, right? There's an amount of confusion in your knowledge about it, which is both bad, it's confusion, good, it's information. It's making anything about it. But the conditional entropy of x given y is the answer to the following game. I give you y first, right? So think of a joint distribution. There's some joint distribution on x and y. So I have a pair x and y. There's some joint distribution D. I give you the y. Tell me what the x is. So the sense is that if I give you y, then because it's a joint distribution, maybe it's giving me some clues about x. Right? In the easiest case, let's say y is equal to x plus 5. So I give you y, you know x immediately. That's a very deterministic relationship. In general, the relationship may be a bit noisier. And so the entropy here captures the amount of noise left in the system after I give you y. Okay? And so the definition of the conditional entropy, let me see if I can do this from first principles, is something like sigma. There's going to be a p of x term here because we have that log of p x given. Okay, the conditional probability of x given. Okay.
Yes.
I think this is right.
Yeah.
So it's the expected value.
It's probably 1 over log or like that.
Sorry?
It's probably 1 over log at this minute.
Oh yeah.
But,
Yeah, no, you're right. It has to be that, right?
but it's okay.
Log 1 over. That's right. Well, yeah. Okay. I should check. I never actually have to write down the explicit expression for this. So, for this, I'm going to make sure I get the right. I don't want to be wrong.
I mean, it's very easy to think about these things now. If you like what you said.
It's not so whatever is incorrect. It is, yeah, it's this. It's with respect to the joint distribution. So the inner term was correct, the outer term was wrong. So it's a sum over x and y, pxy, log 1 over p of x. So this part is correct, but you have to do it over the joint distribution. The expectation is over the joint distribution, not over the marginal x. That's correct. Okay. So this is h of x. All right. So now we can now say, okay, once we have this expression and we have this expression, we can now actually write down what this expression is going to be. And basically, it's going to be something like this. It's equal to sigma over x, sigma over y. Okay. And again, this is just a straightforward computation. If you're wondering where this went, remember that we can always write p of x y is equal to p of x comma y divided by p of y. So that's what's going on here. This quantity here becomes that. And then you subtract these two, you get px down there. So again, this definition and this definition have, maybe this one is a bit more intuitive, this one is not. But let me rewrite this expression. Go back to the KL divergence and observe this. Do the pattern matching on that. What this basically is the Kubla-Hilbert divergence between the joint distribution, let's write it symbolically like this, and the product of the margin. Okay? So this is interesting, because what it's saying is that, when would this be 0? This quantity will be 0 if these two things are equal, right? If we're saying that these two things are equal, we're saying that pxy is equal to px, py. What does this say about x and y if we say this fact?
Independent.
That they're independent. If x and y are independent, if I tell you y, should I expect to know anything about x? If x and y are independent, nothing about y should tell me anything new about x that I didn't already know. So this should be 0. The entropy of x should stay exactly the same as it was before if they're independent. And in fact, that's exactly what will happen. If the two distributions are, if x and y are independent, this is 0, this is 0, which means that there is no information being provided to you about x from y. Okay? That the entropy of x is equal to the conditional entropy of x given y, because nothing has changed. No amount of information has changed. Okay? And notice that it's not hard to see, because of the symmetry of this function, you can rewrite this as this. Doesn't matter which way you write. And you can write it as h of x minus the residual entropy given y, or it's the entropy of y minus the residual entropy given x. It's just the mutual information in between. Okay? Any questions so far? No? Okay. So there are many ways you can interpret this whole thing here. One particularly useful way is, well, there's two ways. One way is via Venn diagram. So let's think of this as a stylized way of representing x, all the information about x, and this is representing all the information about y. Okay? So the amount of information x is h of x, right? Amount of information y is h of y. The mutual information, which is the amount of information one has about the other, is this, right in the middle. Okay? Whatever's left over here, so this is x and this is y, this is h of x given y, this is h of y given x. Okay? And if you add them all up, this whole thing is the joint entropy of h and x and y put together. So from that you can kind of read off these expressions almost directly. So that's a Venn diagram view of the world. But if we do information theory, you always want to think about channels. You have some kind of channel going in. You have X going in, and you have Y coming out. So there's some kind of noisy channel. Right? Information theorists love to think about noisy channels. So you have X going in, you have Y coming out, and Y is somehow noisily related to X. Right? And we want to know exactly how X and Y are related. Well, the answer is that if you think of a big funnel of information coming in, right, which is H of X, okay, then the mutual information IXY is the amount of the information that gets transmitted via Y. So there's a little portion of it that's coming out, which is IXY. What's left over, what you still will never know about X just looking at Y is, and I should have drawn this differently maybe. So we can draw this way. Sorry?
Nothing, I was just guessing that.
Yeah, sorry. Yeah. So there's X coming in. So let's say this is my big pipe coming in. This is H of X. This much goes through to Y, which is I of XY. And the rest of it is H of X given Y, which is extra information about X you cannot capture just from Y. Right? So the channel allows you to suck through IXY, whatever else is what you still don't know about X, even after you read off Y. And similarly the other direction. Think of H of Y, IXY goes back through X, and there's H of Y given X going on. So there's a channel. So in some sense, this is a nice illusion because it makes you feel like information is this physical quantity and you can add and subtract. You can't always do that, but it's convenient to think of it this way. That you have a amount of information, you subtract some of it, and this is what you have left. Okay, so you can almost be, do them, it's almost like a treating like numbers, yes?
If X and Y are independent, then H of X given Y equal to H of X, right?
Yes, correct.
But does it change if they are positively correlated or negatively correlated?
No.
No, the
No.
same, right?
That's the thing, right? So positive and negative correlation is like a second order effect.
Right.
Mutual information is a much more higher order effect. So you're capturing much more with mutual information than you are with just correlations. Correlations are just looking at linear relationships between things. It's a very low order sort of dependency. So things, for example, can have positive mutual information and not even be correlated. You can have weird stuff like that. Because they have positive information at a sort of third or fourth degree level. But pairwise they look independent. So for example, we know how to construct pairwise independent random variables, right?
But mutual information is always positive, no?
It could be zero.
No, I mean, okay, greater than...
That's what I mean. Yeah, it's always positive. But take the example of a collection of pairwise independent variables. Any pair of them are independent. So the correlation will look like there's no correlation. But they're joint, they're not independent. The joint distribution is not independent, so they will have a non-trivial, multi-information. So it's a non-linear higher order sort of way of capturing dependencies among these things. That's one way of thinking. Okay. Any questions so far? So again, what I'm trying to do is give you some algebra essentially to build intuition about the sort of physical meaning of these quantities. And it's helpful to keep that in mind because when you start doing clustering with these things, the form of these expressions won't make sense unless you keep the intuition in your head. Yes.
Not able to figure out how did you come up with this equation?
Which
IXY,
one?
sigma x, sigma y. This one.
This one?
Yes.
From this? Well,
Like,
you just plug in this expression here. This expression is that,
There, okay.
but it's only over x. You sort of have to add an extra summation over y.
That's what.
Yeah, because P, you can think of
X is a marginal.
right, because you can think of P of x as a marginal with respect to y. Right? So P of x is equal to the sum over y, P of x comma y. Right.
Yes.
So whenever you see the P of x in that expression, you replace it by this, and that's where you'll get the double sum that you need. Because that's a sum over x. You'll get the second sum over y. You'll get two double sums. You put them together, and then it'll all work. It does work.
then why it's pxy there?
Pardon me?
Then why is the joint distribution there?
That's the definition.
No, there's a good reason for it. That product can be written as py times px given y.
Correct.
And then it makes sense because you need to go over both variables, x and y.
Yes.
You're given y.
Right.
So if you write it down,
Yeah, so what you're saying is you can write it this way.
yes, then it makes perfect sense. Yes. Because you first observe y, what's the probability that they give you the y?
Yes.
And then what's the probability of x?
The conditional entropy of x given y.
Yes.
Yes. Sure. Sure.
And then it makes sense.
Yes. So in other words, you can think of this as the expected value over y of log of p of x given
Exactly.
y. Yep. Good. So, where were we? Yes. So let me see. Another interesting way to think about this, and we alluded to this very briefly in the communication complexity class last semester that some of you were in, so I'll mention this here, is that you can think of IXY. So we know that if you have h of x, it's like saying, okay, how many, if I play 20 questions with you, how many questions do I need to ask to figure out the value of x? Because there are that many bits in the description of x on average. So on average, I need to ask that many questions, right? So the number of questions is basic entropy. If you think of in the same light, what is mutual information? It's like saying, how many questions do you need to ask to y to get all the information you can get from it about x? So it's a different. So in one sense, I'm just asking questions to x to find out what it is. In this case, I'm asking questions to y to see how much you can give me about x. So obviously, if y and x are independent, there's nothing I can ask y to get about x. So the answer is 0. But if y and x are highly tangled up, they have high mutual information, then I can ask lots of questions to y and get information about x. So you can think of this number of bits, number of yes/no questions I can ask. So that's yet another intuition for what mutual information is telling me. So again, depending on the problem, you pick whichever intuition you want. But that's another way of thinking. Okay. So let's now start getting into actual clustering. Fine. After all this build-up. What I would like to argue that in some ways you can use mutual information as a measure of compression. It is almost like a space unit. It is in terms of number of bits, that's true, but you can think of it as in terms of space. So let's think about this. So let's go back to our basic question of how do I describe the number of clusters, and we said k is the right answer to that. But let's say we don't really have the same number of objects in every cluster. Maybe we have some clusters that are big, some clusters that are small, some clusters that are medium size. And let's say that this one has, I don't know, n1 elements in it, this is n2 elements in it, n3 elements in it, and so on and so forth. And let's just say the fractional sizes of these clusters are p1, which is equal to n1 over n, and this is p2, p3, and so on and so forth, right? I could describe this by the total number of clusters. But since the clusters are different size, if I think of, what is the cluster label for a random point of this, then maybe I don't need to use, k or log k bits to describe this. Maybe I can do something better. And this, in fact, is exact parallel of what you were saying with entropy. You can only use log n bits to describe n items, but maybe you can do better. In this case, the obvious thing to do is to say, well, we'll just look at the entropy of these PIs. You can think of this process saying, take a random point and look at this cluster label. Right. So if many points are on one cluster, you could give that label a shorter description. If there are very few points on one cluster, you give that cluster a longer description. And we know that h of p will give you the correct number of expected bits you need to describe this. So in some sense, before we were assuming that log k was the correct measure of the number of bits needed to describe this. And this is where the compression idea comes in. Thinking of number of bits, you're saying, okay, how much can I compress my representation into? We used log k bits before, and I'm saying, no, I can do better. I can do this. I would get log k bits, for example, if all the clusters are of equal size. Each of size n over k, so each pi was 1 over k, so you get log k. But in this case, I can do better. So we can say that the entropy, we can define the entropy of a clustering, or entropy of a partition really, as this function which is basically normalize the sizes of the clusters and compute the entropy of the resulting probabilities. So we can think of the entropy of a cluster. And here's where things get interesting. In this clustering, we assume that every point belongs to one cluster. We said that. We've always said this for all this time. But suppose we allow clusterings to be soft, that points can belong to multiple clusters, but it can't belong to every cluster. It has to share its contribution. It has a certain budget of contributions of 1, and it can divide that up among different clusters. In particular, let's say that for a given cluster P and a given point X, we can express the probability of a point being in a cluster as the conditional probability of P given X. Okay? With the proviso that the X will basically share its mass among all these things. So this should be equal to 1. Now in that case, what do? What is the notion of the amount of space required to describe a clustering if points can partially unsign themselves? Well, it turns out that the correct generalization of entropy, not surprisingly here, is the mutual information. Remember that all I need to describe mutual information is a joint distribution among two variables. In this case, I am giving you a joint distribution between x and t because I'm describing these conditional probabilities, p of t given x. Right? Again, it could be independent, that's fine, but that's what I have. And to convince you that this is a right generalization, if you now say every p of t given x is either 1 or 0. In other words, if you force the clustering to be a hard clustering, where every point goes to exactly one cluster, and compute this quantity, you'll get exactly h of t. If all assignments are hard. Okay? So in some sense, mutual information is the smooth generalization of the entropy of a clustering, which itself is a generalization of the number of clusters in a clustering when you have softness. And you can test this by saying, okay, what happens if x and t are independent? If x and t are independent, this number is 0. What does that mean? Well, what it's saying is that if x and t are independent, then every point could go to any cluster. Looking at the cluster label, you cannot tell what points it has in it or anything in information. All the clusters are the same. You just have one big cluster. There's no difference between them. They all look the same. And we know that if you put everything in one big cluster, you're not paying any space at all. So then the boundary conditioning kind of works out. In the extreme case, when you have as many points as many clusters as points, then Ixx is basically the entropy of x. You can show this. You just plug in x here, you get h of x minus nothing, which is h of x. So then all the information system just comes from x itself, whatever your random variable x is. That's the other boundary case, where you have as much space as possible to describe x. So what we have here is one half of the equation of a clustering problem. Right? We have a way to describe the space required for a clustering in information theoretic language using mutual information. Namely, it's a mutual information between the objects and their clusters based on the cluster assignment. And this can be hard or soft, it doesn't matter. It's hard, you just get back entropy. If it's soft, you get back mutual. Any questions? So this is a very important step. At least
Can you explain this again?
Okay. Yeah. This is very confusing. The first time I came across this, it took me a while to get my head around this. So once again, the idea is that I want to get an information theoretic interpretation of the number of bits required to describe a cluster. And so I start off by saying, well, if I have k clusters, I need log k bits, because to write on the number k, you need log k bits. And everything in entropy is in terms of bits, so it uses the right units there. Then I said, well, because the clusters are different sizes, we can variably encode the clusters. We don't have to encode them all the same way. We can use, different encodings for different clusters. To model the idea that if you take a random point and look at this cluster label, how many bits do you need? And that gets us to entropy. And then I said, well, if you now say that the cluster assignments don't have to be hard, yes?
But what do you mean you need log k bits to describe the cluster? The clustering is
K, the number k.
log k.
Yes, the number k requires log k bits to describe it.
Yeah, but you don't. Clusters are not just clusters are not just.
But remember how we've started off this whole discussion. What we said was that in all the work we've done so far in choosing k, well, we've said that k itself is a parameter we want to optimize, the number of clusters.
Yeah, but what I'm saying is for each clustering, you need another number of bits to describe it. So it's not just log k.
You have index for clusters.
Yeah. You have an index, you write down the cluster label. I'm looking at the partition, right? I'm saying I partition the input into clusters. So item 1 is cluster 5, item 2 cluster 10, item 3 cluster 20. Write them down. I add up all the bits I need. Now each cluster label can be written with log k bits because there are k
Yeah,
of them.
each cluster label can be written with log k.
But that's a description, right?
Oh, yeah, I agree with that.
But what I'm saying is I don't have to use that, right? That's an upper bound.
Yeah, that's an upper bound.
So, but the actual bound is the entropy. Because I can always do better.
So when you said that you can describe the clustering with log k bits, you mean that each label can be described with log k.
The expected number of bits required to describe a label is log k. Okay. That's the language. In information theory, you always talk about the expected number of something or the other.
Yeah, of course, but then if you have n points, you will need n times log k.
Hence the term expected number of bits to describe a single object.
Yeah.
Yes. Okay. So, so any questions about this transition from here to here to here? Again, this is at least for me, it was a little bit of a tricky transition to make. There's still days when I get up, in a cold sweat and say, I don't understand what this means. And I can't. Okay. So now that we have the first half, if you wish, of the clustering equation, right? We have the space half. The promise I had made to you was that we'd come up with some kind of notion that was comparable, right? So if I'm saying that I can use mutual information here, I expect that I want to use mutual information here. And this is where things get a little more interesting. It gets us into sort of an area of information theory called rate distortion theory. So, if you think of now a channel, right? Again, for talking information theory, you have to say channel every 5 minutes, otherwise I get my card revoked, my information theory card revoked. So, what's coming in is X in this channel. What's coming out is the cluster label. This is my clustering algorithm. And now we can say, well, this is all well and good. But the catch, of course, is that we could just collapse everything in, we could just label T randomly independent of X. That won't be a very good clustering. We've sung this song many times, right? You can't just randomly collapse things. You have this notion of error. So you can talk about error in this context. You can say, okay, I will define some kind of distance function. I don't know what it is. Between a point and the label I get to it. I give some point, I give it some label. There's some notion of a distance between. I don't know what that is. And now I can talk about what the expected error of my channel is going to be. Right? So what's the expected error of my channel going to be? It's going to be basically the sum of, you first pick a point, then you encode it as a certain cluster, and then you pay a certain cost for doing so. So we'll call this the error. Okay, this is summed over all X. This is the total average error of an encoding. Because first of all, what's the probability you see a particular point? What's the probability you transmit? Once you see that, what's the probability you transmit this particular code word for it, T? And what's the error you pay for that? So this is the amount of error I'm going to pay in my system for doing this encoding. So one of the, and we'll call this distortion. That's not about this, we'll call it distortion. Distortion. And so you can ask questions in information theory like, if I want to keep the distortion small, let's say the distortion must be less than some number D, what's the best rate I can get? Right, the best amount of throughput I can get in my channel. And one of the most sort of the deepest results that Shannon showed, right, he showed all these results about information theory, was that somehow the rate of a channel is captured by the mutual information of the channel. That the rate at which you could send information is controlled solely by IXT. In other words, if you say I want to find the best way to communicate X to T, you can think of it this way, that the goal is to minimize that if you compute this quantity such that the distortion is less than or equal to D, this is equal to the best rate. Such that distortion is equal to D. And if you want an analogy that you might remember from the algorithms class, if you remember flows, we talked about min cuts and max flows. The amount of flow you can push through the system is controlled by the smallest choke point of the system, which is the min cut. The amount of information you can transmit to the system is controlled by its choke point, which is the mutual information. This was the big breakthrough of Shannon, that you could express information transfer in terms of this very natural quantity that has this kind of physical interpretation. And this is sort of the start of rate distortion theory. Right? How do you get the best rate for a given distortion? So there's a lot of work goes into basically how to do this in the best way possible with the right encoding scheme and so on. Right? This whole transition from, say, entropy of a channel to Huffman coding is the whole story of information theory. You start off with base concepts like this. How do you make them effective with algorithms to actually do the encoding? Okay. So what this is saying is that if you have some distance function that captures the difference between x and t, right, then you can talk about minimizing this. Why? Because we want to minimize the amount of space we use, because we know this is space, subject to some error constraint. And again, you can write this in a sort of a Lagrangian fashion. You can talk of some energy functional, which is equal to ITX minus some beta times the distortion, which is the expected quantity here. And you can say, I want to minimize this. Right? So this minimizes this and maximizes that, minimizes subject to constraint of that. I should put a plus there. Okay, plus. And then when you work out the details, you can show that, this was shown back in the 70s, that the correct answer for, so the variable here is the actual assignment of points to clusters, which is P of t given x. So you can show that the solution to this has the form where P of t given x is proportional to, that's a proportionality constant here, the weight of the cluster times an exponential minus beta times the distance between x. I'm not going to show you how this works, but you can show this. Of course, this equation is not very useful because this depends on that, and that depends on this. This P of t is equal to the amount of contributions given by. So you have this pair of equations that describes any critical point of this problem, any sort of optimal or critical solution. By just like derivation, you can prove this. And so you need some iterative scheme of equations to solve these things back. So you're getting this, you get this, getting this, you get this. And this intuition is kind of nice right here, because what it's saying is that intuitively, the amount of myself I'm willing to contribute to a cluster relates to my distance from that cluster, but with an exponential backoff. The further away I am, the more exponentially less likely I am to contribute any of my mass to that cluster. Okay, so this is rate distortion theory, and this is all well and good. What it doesn't give you is a way to, you have to come up with this D yourself, some kind of natural distance function between points and clusters. That's something you have to choose. Okay? And this, in fact, finally brings us to the information bottleneck method, which is the method that started off this whole discussion. How to do information theory. So this is called the information. And what it now is going to show us, after all this sort of background information theory, is how to actually construct a clustering method, a formulation, that uses this intuition without having to deal with all these problems. And it's actually a very clean method. So, any question? I'm going to round this out here. Okay. Think of X and now being documents. This sort of first came up in the context of text clustering. So let's think of X as documents. What we want to do to apply the principles of rate distortion theory is to come up with some notion of a distance between points and clusters that allow us to do all this machinery. So that gives us these things which are basically our cluster assignments. And we don't yet know that even how to do that. But here's what we're going to do. Suppose we have a problem where we have a matrix given to us. So we have an X and a Y. You can think of each row as an object in your space. Okay? So So think of anything as a document, let's say, any one row is a document. And you can think of y as your dimensions of your space, your features. So maybe these are words, word counts. So anyone think here, tell us. And let's normalize all this. So think of this as some kind of joint distribution between x and y. So joint distribution between the documents and the features. Right? One way to interpret this is that, given a particular document, P of y given x is the conditional probability of seeing a particular word given the document. Or you could think of it as a whole vector. Think of those numbers as the vector describing x, any particular x.
What do you prefer to be about?
No, it's given to you, it's the input. Your input is a matrix of this form, normalized appropriately. Yes? So that's given to you. And now you want to do this clustering. Okay? So here's what we're going to do. If we think of clustering x into t, what are we doing? We're saying, okay, I'm going to put these two rows in one cluster, or I'm going to put half of this row and half of this row into one cluster if there's a soft assignment. And I'm going to get some new matrix after my clustering, which looks like t times y. Right? And there's some transfer process, p of t given x, that goes from x to t. And again, remember, these are not just unions of these things, they could be merged in some complicated way. Half of this, 1/3 of that, whatever. Okay. So what do you want? What you want to say is that with respect to y, this looks pretty much like this. In other words, whatever information was in the system, you want that information to be preserved here. Okay. In other words, since we know the information in the system, this joint system, can be expressed as ixy, we want ity to be as close to ixy as possible. Okay? Because this somehow captures the fidelity of the new system with respect to the old system. Okay, this is so does it make sense? This transition here? Okay. So what next? One thing that's very interesting, if you see what is so if I think of this way, I can now think of P of y given t. So if P of y given x was the coordinates of x, what is P of y given t? What is this? What is the physical interpretation of P of y given t, this rho?
The probability that those features describe the cluster T.
I know, but in a sort of physical sense, and if you have points in a space, what does this somewhat capture? This thing would capture the description of the center of the cluster T. Right? This is the descriptor for T. If for x there was a descriptor for each point, for T there's a descriptor for that cluster center. Okay? And the reason why I want to point this out is because I want to rewrite this expression ity in another way, in a yet another way. So let me write ity. This is sigma. Let me see how I do this. I want to say it as t and y. P of t comma y log of P of t comma y over P of t, P of y, right? Okay. So now what I'm going to do is I'm going to simplify this expression. I'm going to rewrite this as, I'm going to remove this, I'm going to remove this. Okay. And I'm going to rewrite this as okay. Now P of t I can take out. Okay. What is this expression? Okay. Read this again, one more time using the KL divergence. Now, what is this expression here? First of all, note that, so let's first note that P of y is equal to sigma over T, P of T, P of y given. Okay, just by basic calculation. Okay. Now, if you thought of this not as probabilities anymore, now this is a bit of a mental jugglery you have to do now. Think of this as a vector. It's a vector over y, right? For each value of t, fix the value of t, and for each particular value of y, there's a coordinate, right? This is P of y given t, yes? The same thing is true for this. This is some kind of coordinate, which is basically the aggregate sum of all these things, the average of all these things. Because you take the average of all these individual coordinates, individual points. So if you think of this as a point, and this is a point, what is this quantity saying? This quantity is the, if you think of all my pyt's at different places, so this is py given t1, this is p of y given t2, this is p of y given t3, and so on. Then the centroid of all these points is py. It's the average of the coordinates of all these points. Okay. If I want to maximize this quantity, I want to make this as large as possible, what am I saying here, geometrically? I'm saying that this number equals to the average distance of these points from their centroid. I want to make this big. What does that mean I have to do? Yeah?
Does it mean the points are as close to the centroid as possible?
If they're as close, then these distances will be small. Then this number will be small. So it's the opposite. So they have to be
Far away.
as far away. But these are cluster centers, right? What do we like from our cluster centers in general? Any clustering problem? We want our cluster centers to be? So somehow the information theoretic statement of this matrix should capture this matrix has become a geometric statement about cluster centers being far away, where far away is again measured information theoretically using the Kullback evaluations. So there is a geometry here, but it's hiding underneath. You're going to have to pull it out of the whole expression. And because I can't think about anything unless I make it geometric, this is how I think about information theory. It's all in terms of this, the underlying geometry of these distances. Okay? So what we're saying is that we want to compress, and here we want to pull the clusters far apart. That makes sense now. Now this all starts making sense. They're all, these two things will compete in the right way. Pulling them apart will make the error better, but it will also make them hard to compact the clusters, and there'll be a nice balance point. So now we're ready to actually finally write the clustering function that we want. So now we can define some energy functional that says we want to minimize this quantity, right? That was the compression cost. And we want to maximize this quantity. So we put a minus sign, we're going to maximize it. And now we're in actually pretty good shape because we have two quantities that are commensurate to each other. They're both information, they're both mutual information, they're both in terms of bits, expected number of bits needed for something. And again, this quantity we compute because we have this variable P of t given x, which is the cluster assignments, which is the unknown. And of course, once you have P of t of x, P of t is equal to sigma over all x, P of x, P of t given x. And once you have that, you can compute P of y in the following manner. And this is equal to
The sum over x's or y.
it's basically 1 over P of t, sum over all x, P of x comma y comma t, which is equal to 1 over P of t, summation over all x, P of x comma y, and this is something I'm going to do here, which is a little bit, you be careful about. This system essentially gives you what is called a sort of a Markovian assumption that x is sufficient to get t. You don't need to know y. So in other words, given x, t and y are conditionally independent. Because once I have x, I can find t. I don't need to know y. So that's why I can express this quantity as this quantity here. So I'm not done yet. All I told you was, oh, once I have this, I can find this and this. In other words, I can find the weight of a cluster, the number of points in a cluster, and I can find the cluster coordinates, which is this. Right? But I still don't want to find this. But it turns out, and this goes back to, again, the rate distortion theory idea, that using the same principles used to solve the rate distortion problem, and observe that functional form there, it's going to be very similar, you can rewrite this expression, P of tx, as it's something proportional to P of t exponent minus d beta x comma t, just like before. With the difference is that now I can tell you what d is. dx comma t is equal to the KL divergence between these two objects. What are the two objects? P of y given x and P of y given t. Sorry. Y. And again, to make any sense out of this, think about what I said. P of y given x is the coordinates of x. It's the point that describes x in the original data. P of y given t is the coordinates of the center used to describe the center x was assigned to. Right? So what is this number? It's the distance between the point and its cluster center. Well, that makes sense. That's how we expect these things to work. But the distance now, instead of being something you impose from the outside, is the KL divergence. It just sort of pops out naturally from using visual information. And people who wrote this said it all came out naturally by magic. Really, it's not magic. It's just that you are implying underlying geometry with the KL divergence, which is why it shows up. So essentially, by giving a purely information theoretic formulation of the clustering problem, minimize this quantity. Right? You get a way of defining clusters, cluster centers, and points and distances that is very much like what we've seen for K-means and for Gaussians, but using equivalent linear divergence as our geometry. The advantage is that now these two quantities are an equal figure. They're comparable. Now, of course, there's no closed form for this. These are nonlinear, non-convex problems. So in effect, what you do is you start off with some guess for this, you solve for this, you solve for this, and you go back and solve again for that because now you have this quantity, and you just do this over and over again, just like a k-means, like an EM type method, and you can show this will converge and will stop at some point. Yes.
So how does it compare to k-means, for example, practically?
So it depends on the problem. So for things like word vector clustering, where there's no reason to believe that, say, an L2 assumption of the distance space is reasonable, this in fact is better because it implies a kind of multinomial assumption, which is more reasonable for things like words. So I've actually used this in a couple of papers for problems involving text, and it works much better than an L2 based solution. But so it's really well suited for those kinds of problems, where you believe that the natural underlying shape of the space is not Euclidean.
You said the word to where? So the
Word vectors are the representations.
How that's the input.
Yeah. Yeah, so for example, so Y was a collection of words and X was frequency constant. So each document had a frequency constant, the usual bag of words. Yeah, exactly. TF-IDF type stuff. So what is that? So yeah, I'm not. So I think I'm going to continue this next time because I'm not fully done with what I want to tell you. There's some very nice properties of this thing. I want to point out one thing to you. That again, nowhere in this I'd actually tell you how many clusters there were.
Can I ask them?
1 second. Okay, so you can, we'll talk about algorithms for how to solve these things next time. And for some of the algorithms, you need to specify a certain number of clusters, but there's nothing stopping you in this formulation from having an infinite number of clusters and letting the system kind of figure out what it needs to do. And so there's some very nice properties of the, so we talked about hierarchical clustering and sort of getting a continuum over the space of clustering. You get that with this very nicely, and that's what I want to talk about when we solve this next. You had a question?
Yes. What if the spaces, the y, the dimension of y's are different?
What does that mean?
So the input space,
Yeah.
the dimension of the input y, or the features,
Yeah.
let's say is y.
One. There's one. There's one number for everything. Yes. Okay. Then you can't do this. Then you can't. This doesn't work.
Or let's say they're different, right? I wanted to give
You mean it's heterogeneous?
Huh?
You mean it's heterogeneous?
Yeah.
The different kinds of y's?
Yeah, let's say that let's say that I give let's say that I give you a sequence of 5 words,
Yeah.
okay? And a word. So the x would be a word and the y would be a sequence of 5 words.
Okay.
So how this word appears in the context, okay? And then let's say I want to learn the representation for this word through reusing it.
Okay.
You see what I'm saying?
No.
So the deep learning people have done this called word to act, right?
Yeah.
Which basically they use the context of the word to learn the
Yeah, but
representations.
I want to point out one thing. This is not about learning representations yet.
Yeah, that's what I'm saying. Like, can you do this?
If you believe that clustering is a way of learning a representation, then maybe. But this is not the same thing. I mean, there's a sense in which T is your representation.
Yeah.
So you could think of clustering as learning this representation. So then I'm not sure what your question is now.
No, I'm just
So in a
saying.
trivial sense, yes. This could think of this as learning
Like,
representation.
in most scenarios, y's are different than.
Yeah, but I don't know what you mean by y's are different. Are they different? Is each dimension a different object? Are they apples and oranges? Is what you're saying? Or they're just, what do you mean by different? I don't say anything about the y. Y could be anything. I could actually, in fact, I can stick on different kinds of y's here. And this whole thing still works. In fact, I've used this idea. That you can say, this first set of y's are text-based things, the second set of y's are some other features, this third set of y's are some other features, and then put the whole thing together in one big thing. You can do that. There's nothing stop. The mathematics of this does not prescribe you from doing that. If that's what your question is.
I still end up with this high dimensional y.
Sure. That's a different question. The question of high dimensionality is a different question altogether. But I'm not even talking about that right now. I'm not talking about complexity or issues of representation or how you even compute these properties in the first place. That's a different story altogether. Right now, I'm just looking at the representation question. The basic abstraction of how you do this information theory. There are lots of other good questions about how you do this. And algorithmically, yes. But for now, we're not worried about that. Okay, any other questions? Okay, so next time we will see more about this, and in particular we will see how this formulation, which I personally quite like, so lends itself to sort of nice ways of thinking about the space of all clustering in a way that you can't do with some other.